In this video, we're going to talk about molecular geometry. Molecular geometry is basically exactly what it sounds like, the geometry of molecules, or the shape of molecules. Molecules, if you remember, are groups of atoms that are covalently bonded together, and drawing their electron dot structure is something that we learned last week. Unfortunately, electron dot structures don't really show us a good three-dimensional structure for a molecule. It shows us how the molecule is generally arranged with a central atom and how many bonds there are on the central atom and how many lone pairs. But it doesn't give us a good idea of the three-dimensional structure of the molecule, or the molecule's geometry. In order to predict what shape a molecule has, you basically have to do two things. The first is draw its dot structure. This is something that you already know how to do. The second is to determine how many bonding groups of electrons and how many lone pairs of electrons are on the central atom. The example here is sulfur dioxide. If you look at the electron dot structure for sulfur dioxide, we can count that there are two bonding groups, the double bond and the single bond. Single, double, and triple covalent bonds all count as one bonding group. We can also see that on the sulfur there's one lone pair of electrons. If you're able to do these two steps, draw the dot structure, and count those two electron groups around a central atom, predicting the geometry of a molecule is very simple. On the molecular geometry chart that you have in front of you, for each of the geometries, we are going to fill in how many bonding groups of electrons and how many lone pairs of electrons are necessary to be on the central atom to have that particular geometry. The first that we're going to do is two bonding groups, 0 lone pairs. With two bonding groups and 0 lone pairs, we get an electron geometry and a molecule geometry that is linear. And you can see from the shape of the molecule why it is called linear. It's basically a straight line. The bond angle here is exactly 180 degrees between the two atoms that are bonded to the central atom. If I add another electron group as a bond, now we have 3 bonding groups, 0 lone pairs. The electron and molecule geometry have changed now. We get an electron geometry called trigonal planar, which basically translates to a triangle that is flat. And you can see from the molecule, the 3 outer atoms make a triangular shape, and if I rotate the molecule, we can see that it is in fact a flat molecule, or planar. The bond angle between each of those atoms is exactly 120 degrees. Now, I'm going to remove one of these bonding groups of electrons and replace it with a lone pair of electrons. What we should see is that the electron geometry, in other words, the geometry of the electron groups around the central atom, is still trigonal planar. They are still in a triangular shape, and they are still flat. However, the molecule geometry has changed. This molecule geometry is called bent. The reason the molecule geometry has a different name from the electron geometry is because when we look at this molecule, we would not actually see the lone pair of electrons. They're too small to actually see. What we would see is this, a molecule with 2 bonded atoms to the central atom that is no longer linear, but in a bent shape. The bond angle here says it's 120 degrees. It is close to 120, but it's actually slightly less than 120. I'm going to remove my lone pair, put a bonding group back on. I'm going to add one more bonding group to give us 4 bonding groups. Now with 4 bonding groups, 0 lone pairs, we have an electron and molecule geometry called tetrahedral. Tetrahedral basically means 4-sided. If we were to put faces on each of the sides of this molecule, we would basically have a triangular pyramid, or a 4-sided prism. The bond angles between each of the atoms is now 109.5 degrees. No matter how I rotate the molecule, we can see that the bond angle is exactly 109.5 degrees on every side. This is due to the fact that the electron groups around the central atom are repelling each other. They are all negatively charged, so they're trying to move as far away from each other as possible. And in fact, as we build more and more complex molecules, you'll see how that influences the molecular geometry of the molecule itself. All right, I'm going to remove one of these bonding groups and replace it with a lone pair. The electron geometry remains tetrahedral because we still have 4 electron groups, but now with 3 bonding groups, one lone pair, our molecule geometry is called trigonal pyramidal. Trigonal because we see a triangular shape with the outer atoms. Pyramidal because they are no longer on the same plane, but they are slightly raised, kind of like a tripod. It says the bond angle is 109.5. In reality, it's slightly less than 109.5. If I remove one more bonding group, replace it with a lone pair, we get the same electron geometry, still tetrahedral because there are 4 electron groups. But with 2 bonds and 2 lone pairs, our molecule geometry is now bent. We saw bent earlier with 2 bonds, 1 lone pair. We see bent again with 2 bonds, 2 lone pairs. In fact, some geometries will repeat themselves depending on the number of bonding groups and lone pairs. The bond angle here is 109.5. In reality, it's actually slightly less than 109.5. I'm going to remove those lone pairs, add back my bonding groups. Now I'm going to add a 5th electron group as a bond. We're going to see a little bit more complex molecule shape that we call trigonal bipyramidal. This would be 1, 2, 3, 4, 5 bonding groups, 0 lone pairs. The electron and molecule geometry are the same. Trigonal bipyramidal. Trigonal because, again, we can look at the molecule and see a triangular shape with some of the outer atoms. Bipyramidal because we could build a pyramid going up to the top bond or down to the bottom bond. So basically 2 pyramids set bottom to bottom. Now we actually have 2 bond angles with this molecule. We have a 90 degree between the 2 axial bonds. And then if we rotate the molecule, we can see that there's a 120 degree bond angle between the equatorial bonds. Axial and equatorial, just ways that we distinguish between the different bonds on the molecule. I'm going to remove one of these bonding groups and place a lone pair. We get the same electron geometry, trigonal bipyramidal. However, our molecule geometry now is called seesaw. Very creative, I know. We can rotate the molecule and see why it gets its characteristic name. We have 2 bonds that are at 120 degrees from each other. Then we have another 2 bonds that are 180 degrees from each other. And if we just look at it the right way, it kind of looks like a seesaw that can move up and down. The other bond angles that we still see are 90 degrees. And the 120 is actually a little bit less than 120 because of the lone pair on the top of the molecule. If I remove one more bonding group and replace it with the lone pair, now we have 3 bonds, 2 lone pairs. If I can get this guy to rotate. The electron geometry is still trigonal bipyramidal. The molecule geometry now is T-shaped, so named because it looks like a capital T. Bond angles here are 90 degrees. You could even say there's a 180 degree bond angle between the top 2 bonds. I'm going to remove one more bonding group and replace with a lone pair. Again, our electron geometry is trigonal bipyramidal, but now that we have 2 bonding groups, 3 lone pairs, our molecule geometry is linear. So we saw linear earlier when we had 2 bonds, 0 lone pairs. We get linear again with 2 bonds, 3 lone pairs. Bond angle here, exactly 180 degrees. All right, I'm going to add one more bonding group, or one more electron group as a bonding group. This will be the most complex geometry that we'll deal with. 6 electron groups around the central atom. With 6 bonds, 0 lone pairs, the electron and molecule geometry are both what we call octahedral. Everywhere we look on the molecule, the bond angle is exactly 90 degrees. If I take away one of the bonding groups and replace it with a lone pair, our electron geometry remains octahedral, but our molecule geometry is now square pyramidal. And we can see from the molecule itself, it kind of makes a square pyramid. Looking down from the top, we can see the square. And if we connect each of those outer atoms to the top one, it would make a square pyramid. Bond angles here are all 90 degrees. Removing one more of the bonding groups and replacing with a lone pair, the electron geometry again remains octahedral, but our molecule geometry is now square planar. So named because we can see square, the outer atoms, and they are all on the same plane. basically a flat square. Bond angles here would be 90 degrees. You could also say a 180-degree bond angle if we were going across the molecule. Okay, so flipping to the next page of your notes, you should see a table that looks like this. We have taught you how to draw electron dot structures, shown over here on the right, as the ammonia molecule. We're also going to learn how to draw what we call 3D dot structures. In a 3D dot structure, we try to show the three-dimensional arrangement of the bonds on the central atom. In this case, ammonia has a trigonal pyramidal geometry. In other words, it kind of looks like a tripod. The electron dot structure does not do a very good job of showing that tripod shape. So we use a 3D dot structure to try to show three-dimensional shapes. The wedge triangle here shows a hydrogen that is bonded to the nitrogen and pointing towards us out of the plane of the paper. A dashed triangle shows a bond on a hydrogen pointed away from us out of the plane of the paper. So if you imagine a tripod, one of the legs of the tripod can be in the plane of the paper, one will point towards us, and one will point away from us. When drawing a 3D dot structure, we try to represent any bonds that are not on the plane of the paper or are pointed towards or away from us. This takes a little bit of practice, and it helps if you have the 3D model in front of you to kind of draw according to. So let's see what that looks like. If we drew the electron dot structure for CH4, we would get this structure. Basically, it looks like a T. However, this structure doesn't really show us the three-dimensional structure. We can determine what the geometry is, though, by referring back to our chart. Here I can count 1, 2, 3, 4 bonding groups, 0 lone pairs on the carbon. If we go to our chart, a 4, 0 gives us a tetrahedral shape with a bond angle of 109.5. Now, tetrahedral doesn't look anything like this structure. In fact, tetrahedral shapes look something like this. We have 1, 2 bonds that can lie in the same plane, or the plane of the paper. We have 1 bond pointed towards us, 1 bond pointed away from us. So if we were to draw a 3D dot structure, the bond on top and the bond to the left could be represented just as lines, because they are in the same plane. The bond pointed towards us, we would draw a wedge. The bond pointed away from us, we would draw a dash. So our 3D dot structure would end up looking like this. 1 hydrogen on top and 1 hydrogen to the left all fall in the same plane. 1 hydrogen pointed towards us, 1 hydrogen pointed away from us. So in this way, our 3D dot structure gives us a better idea of what the actual molecule geometry is. Now, let's say we had a molecule that had more than one central atom. We can actually determine what the geometry is around each central atom. In this molecule, oxygen and chlorine, denoted as 1 and 2, have separate and individual geometries around them. We can determine each geometry by simply following the same steps. Count how many bonding groups and how many lone pairs there are around that atom. We can then refer to our geometry chart to determine what the geometry is. So for number 1, I see there are 1, 2 bonding groups around the oxygen and 1, 2 lone pairs around the oxygen. If I refer to my geometry chart, that would give me a bent geometry. Similarly for the chlorine, I have 1, 2, 3 bonding groups, 1 lone pair. 3 and 1 gives me a geometry of trigonal pyramidal. Let's do another example. Here I have a carbon central atom and an oxygen central atom. Carbon has 1, 2, 3, 4 bonding groups, 0 lone pairs. A 4, 0 gives us a geometry of tetrahedral. For the oxygen, again, we have 1, 2 bonding groups, 1, 2 lone pairs. 2 and 2 give us a bent geometry. Here we have a carbon that has a single and a triple bond. Remember, triple bonds and single bonds all just contribute as one bonding group. So here I would say this carbon has 1, 2 bonding groups, 0 lone pairs, which would give us a geometry of linear. Why don't you try 6, 7, and 8 on your own, and you can check those with your teacher in class.